Hi all, welcome to part 5 of the lecture on sequential circuits. So far, from part 1 to 4, what we were discussing is about the latches, and it's a very basic fundamental storage element, right? So that is what is your understanding, and we already saw how to construct a typical memory element which can store a single bit of information. That is what we call as a latch. Using two basic configuration, that is cross coupled NAND gate connection and cross coupled NOR gate connection, right? So this is what we seen. So just a summary of it, and some of its variations too we will see here. So a storage element in a digital circuit can maintain a binary state indefinitely, right? So that is what we've seen. So it's how it is maintaining. So this maintain or the retain state is something interesting. That means when the input to the circuit is like a 0 0, it is in the no change state. So that is a default thing, right? So it can maintain a binary information indefinitely, but we saw that that I have to clarify. I will tell you. So in general, this is a requirement. So indefinitely until directed by an input signal to switch the state. I mean, when the input changes, accordingly it will change. If the what the input is saying, whether to set the circuit or reset the circuit, accordingly it will change. But otherwise, it will maintain in a particular state indefinitely, right? And what is that input for retain information? That is actually varying for a SR latch and S bar R bar latch, but we can uniform the case that we will see. So how to make it a common configuration for doing both. So the major differences among various types of storage elements are in the number of inputs they possess and the manner in which the inputs affect the binary state, and we will see how different latches devices are varying from one to another. The storage elements that operate with signal levels are referred to as latches, and we will see what is how this there is another category of storage element, I mean memory element, called flip flop, and how it is different from latch we will see. So typically we have a concept of clock, and these latches are supposed to respond only on the level of a clock, where flip flop are something that can respond to an edge of a clock, and this concept we will see. So that is the main difference between these two devices. So typically latches are enabled by some enable input, so that we don't want it to be a clock signal, right? Where flip flops are nothing but clocked latches. So like that you can understand, and we will see that. So before moving on to more details, I just want to clarify something. See, this is a two basic configuration we saw already, the cross coupled NAND gate connection and the cross coupled NOR gate connection. So here you have a Q and Q bar, the main output, and its complementary output, right? See, now hope you remember the characteristic table or truth table also, right? So how was it like when you are applying S and R? What is the response? So there are four cases like 0 0, 0 1, 1 0, 1 1. So 0 0, it corresponds to, for cross coupled NOR gate. I mean this was your so I'm not going to explain this again. This is because in the last video lectures I explained this in very detail. S bar R bar latch, right? So S bar R bar latch, it is something that is activated when this S is having a low value, so active low latch. So when S is equal to 0, that means you want to set the circuit, right? So this corresponds to set the circuit, so that this Q will be 1, and R is equal to 0 is for resetting the circuit, so that the output will be 0, and this 0 0 here is forbidden. Okay, let me write the case. So you will get the output as something 1, but we will not allow this, so we can call it as forbidden state. So this corresponds to set, and this corresponds to reset, and this 1 1 corresponds to retain the information, right? So this is your memory or latching the information, right? So this corresponds to retain. So this is what we saw already. I'm not explaining, okay? So please watch the previous video for the detailed explanation, like how these the circuit is behaving to these different inputs. Now we similarly we saw another circuit called the cross coupled NOR gate connection. I think this is with what we started with. So this is an active high circuit, where when you, so typically so sometimes as the first input is R is what is connected to Q. Some people call it as RS latch also, RS latch or SR latch, whatever it is. So RS latch, you can remember like that, because so that the first input should be R, but here it is SR, like that we are connecting. Here we are connecting like RS. Okay. Anyways, or SR latch also, both are fine. Some textbook they are using this name. So when S is equal to okay, different cases like S is equal to 0 0 0 1 1 0 1 1. How the circuit is working? Again, I am not explaining. The output is like the 0 0 here corresponds to retain. Okay, and we already seen how this retaining is happening, and 0 1 corresponds to what? 0 1 corresponds to, so when S is equal to 0 and R is equal to 1, R is equal to 1 is for resetting the circuit. So just opposite to what we seen in cross coupled NAND. And similarly this S is equal to 1 for setting the circuit. So this is setting the circuit, and this corresponds to the forbidden state. Okay, so this is not allowed. And now you have to understand clearly. So which could be the default behavior you will be expecting, like the cross coupled NAND gate connection, or the cross coupled NOR latch, which will be your default expectation. So why I am saying is like active high is right. So that is something by default come to our mind most of the time, because so this is something more meaningful for us to explain, and for us to keep in our mind, like when S is equal to 1, I want to set the circuit, so it's meaningful, right? So here also, here it is active low, so that is why it's behaving just opposite to this. Similarly, when R is equal to 1, I want to reset the circuit. When both inputs are 0 0 means when there is no power and all, I want to retain the information in a computer memory, right? So it's more meaningful. And 1 is something forbidden, like that. But here things are just opposite, right? When S is equal to 0, I want to set the circuit. So because it is active low, S is equal to 0, on background S bar is 1, right? So that is why we are giving this name. And when R is equal to 0, we want to reset the circuit, right? So and retaining also in 1 1. So this is something important. So this behavior, right? So what people are doing is most of the cases, basically latch we have a 2 configuration, let it be there stable. But when it comes to flip flop and other devices, and especially we will see something called latch with enable circuit, we are going to see that, and there everywhere we will maintain this as the behavior. So this is something default that is coming to everybody's mind. Okay, so basically we have 2 variation as latch, cross coupled NAND and cross coupled NOR, respectively known to be the active high latch, that is RS latch, and active low latch, that is S bar R bar latch. But when so that is at this point this difference is there, and rest of the explanation we are going to see in flip flop and latch with enable everywhere. This will be the default behavior we will be seeing for this SR latch or SR flip flop. So let me explain that. So here you can see the same cross coupled NOR gate. I am trying to make the behavior something like what we seen lastly. So what I added extra here is the enable input. Okay, so enable input is something I added, and I want to activate the circuit. So this is your SR latch with the enable input. Okay, that's all, with the enable input. So compared to the previous diagram, the only difference is I added something called an enable input. Now how to pass this enable information into that basis? So basically I just want to keep this implementation as it is. So this is your basic cross coupled NOR connection, something we already analyzed in details. That is there as the basic thing on the background, and in addition to that we added this enable. So enable is there, and we have the inputs S and R and the output Q and Q complement, like that. Now enable, whenever this enable is low, I don't want to activate the circuit, so let it be active high circuit by default. Okay, so whenever enable is 0, whatever be your S and R, I don't want to activate the circuit, in the sense I don't want to reset or set nothing, simply I want to retain the last information I am having. Okay, so let me, so typically at in the clock cycle something Qn you can denote, or simply okay, I just want to retain the last information, let me denote like that. Okay, so this is what I call as the retain stage. Retain stage, or you can call it as retain stage, is otherwise called the memory part, or the latching, right? In any ways we can call the information is kept as it is, that's all. So whenever this enable is 1, I want to activate the flip flop in such a way that so what I want is now I am going to fix the behavior. See, 0, the inputs are like 0, 0, 0, 1, 1, 0, 1, 1. Okay, so these are all the, so we have 4 types of input to this S and R: 0, 0, 0, 1, 1, 0, and 1, 1. Now, in all these 4 cases, I want to enable the circuit, then only I want the response. If it is 0, whatever be the input, the circuit simply says this you know, right? They don't care, right? So I'm not caring the input, whatever it is. I want to retain the last information. Now I am fixing the behavior. See, enable is active, so the circuit will be working. So when R is equal to 1 and S equal to 0, what is the behavior I need? I want to, R is equal to 1, I want to reset the circuit. Okay, so this is your reset. And when S is equal to 1, definitely R is equal to 0, I want to set the circuit, right? Now when both are 0, 0, again I want to retain the circuit. Retain means this. And when both 1, 1, let me not allow this input for the time being, and we will see the variation where this 1, 1 is allowed in flip-flop. Okay. Anyways, latch up to this is what we are having. So that about it. Okay. Now what I done is, without analyzing the circuit, directly I fix the circuit. I fix the characteristic table. Now you have to verify, right? Is it the correct behavior of the circuit or not? Okay, I'm telling you this is the behavior, but you have to verify. So the construction is made in such a way that first we fix a behavior, accordingly we have had that construction. So that is the actual thing happened. Okay, anyways, let's see whether it is correct or not. So I will just tell you a few cases. So let me see. Let's see what about this. Say when S is equal to 0, I'm just randomly picking this. Enable is 1. Okay, so this second row, not second row, third row. Enable is 1, and you can see that S is 0. And R is 1. So this is the input I given. Now you can see that this is your AND gate, right? So when for AND gate both inputs are 1, the output will be 1. One of the input is 0, output will be 0. Okay. Now you can see inside this we have the cross coupled NOR gate configuration where first input is 1. And this is something we already seen. The first input is 1 and the first input is your R, right? R is 1 and S is 0. The output of this cross coupled NOR gate is 0. Okay, so this one you know already. So accordingly you can conclude so that you are getting the output as 0. So this is the behavior it's showing, right? Fine. And if you want to analyze it further, I will just tell you, because something we already seen. I was trying to skip it, because for NOR gate one of the input is 1. Right, NOR gate, one of the input is 1. Whatever be the other input, so some Q is coming here, whatever it is, one of the input is 1 means the OR gate will work, that is 1, and NOR, negation of it, the NOR gate will output you 0. And this 0 is coming here, right? So this 0 is coming here, and 0, 0, both inputs, output of NOR gate is 1. So this is what we see. So that case is correct, right? So let me now remove this. Similarly, it will work for that set case also. Now let's see whether it is retaining information in this particular case. Okay, so this is very simple, because enable is 1 and these two things are 0, 0, and when inputs are 0, 0, the AND gate is going to output you 0, 0. Okay. And 1 second. Yes, when R is equal to 0 and S is equal to 0, the AND gates are giving output as 0, 0, and for the cross coupled NOR gate connection, when the inputs are 0, 0, you can see that, see this first row, it is retaining the information. So that is what we are getting also, right? So this is actually, this is very simple, because I just added on further level of AND gate, AND gate only, and the output of the AND gate is nothing but the input as it is, right? So this is the observation you can see. So it is just your cross coupled NOR gate connection only. So here you are having this R as it is, because whenever this enable is equal to 1, this R will be propagated here as it is, and similarly whenever enable is equal to 1, this S will be propagated as it is. This is your basic cross coupled NOR gate connection only, so it will behave like it. So anyway, so this is the default behavior, and that is what we are getting also. Fine. Now this is something tricky, because in the cross coupled inside this small circuit was your active low latch, right? Your S bar R bar latch. Now using that also we are trying to get that default behavior, and see, and what is our default behavior? Enable, let it be there, S and R, and your output to Q, right? So whenever enable is 0, whatever be your input, by default we are assuming active high enable. That is why we want to retain the information. And whenever enable is equal to 1, let's fix the cases. 0 0 0 1 1 0 and 1 1, and in all the cases enable, let it be 1. And the default behavior here also I just want to maintain as this, right? Okay, so that's the default behavior I want. So when this input is 0 0, I want to retain information, but S bar R bar latch is behaving something differently, but using that one more level of NAND gate we can achieve this. So this R is equal to 1, I want to reset the circuit, right? I want to reset the circuit. S is equal to 1, I want to set the circuit. And this is something I can I will be I will not be allowing, okay, forbidden state. Yeah, that about it. And let's see whether it is behaving like this or not. So here it is like S and R and enable input. Okay, now let's analyze. So this is your, again this is also your SR latch with enable input. But what is the difference between this one and the previous one? Here this is made out of cross-coupled NOR gate, where this is made out of cross-coupled NOR gate. NAND gate, sorry. Or SR latch and S bar R bar latch. Okay. Yeah, I am not writing that, you know it, right? So let's see that. See the first some case, let us randomly choose the set case, let's take. Okay. So when enable is 1, S is equal to 1 and R is equal to 0, you can see that here you have the NAND gate. See, let me number them. NAND gate 1, 2. In exam also you can number like this, and using this you can explain. Okay. So NAND gate 1, the output is, both inputs are 1, right? So NAND gate 1 is going to give an output that is 0, and this one is going to give you an output 1. Fine. Now you have to analyze your the cross coupled NAND connection, where what I remember, here you have S and R, right? This S and R, and you are getting like S is equal to 0 and R is equal to 1. S is equal to 0 for setting the circuit. Hope you remember, because it is active low. So cross coupled NAND, this will output this as 1, and that one is what is shown here. Fine. Or you can see how it is happening, because for NAND gate, when one of the input is 0, definitely the output will be 0 1, right? And that one will be coming here, and 1 1, the output will be 0, right? That's all. So see how it is behaving. That one more level of NAND gate is achieving it. Let me remove this part, and let's see this case, right? This was something different for our cross coupled, not only this, everything you have to analyze the remaining cases also. So this whenever this enable is 1 and both S is equal to 0 and R is equal to 0, what is the output? Irrespective of this enable, whatever it is, one of the input is 0, right? So NAND gate will output as 1 1. So 1 1 for the cross coupled NAND gate, this 1 1 was your retain, right? And that retain will happen here now. So here for 0 0, that retain will happen, because when actual input is 0 0, inside this cross coupled NAND will get input 1 1. So that is the thing. So some kind of negation is happening, and that will help the performance. So it is actually your S bar R bar only. So that is a conclusion. So whenever this enable is active, whatever be your S, this enable is active, right? So enable is active means the other input, the output depends on the other input, right? So the other input, if it is 0, it will output as 1. If S is equal to 1, it will output as 0. So what I can conclude, whenever I am fixing this enable as 1, enable as 1, I can see that this output, the first NAND gate is giving me an output that is S bar, because when s is equal to 0, this will give me 1. When s is equal to 1, this will give me 0, right? So this is just complement of the input, and here I am getting r bar. So now this is your s bar r bar latch. So it will behave like an s bar r bar latch. That is fine. But outside I am having s and r. So finally I am getting sr, I mean the default behavior I am getting. But instead that I am using the s bar r bar latch. So hope it is clear, right? So now I given you the basic configuration and its explanation in the previous video lectures, and hope you have an idea on this truth table. We saw this in detail. Now what I done is simply I added an enable input along with the circuit. Now to support this enable for cross coupled NOR gate, we added 2 AND gates, so that it will simply output the input as it is whenever that enable is 1. And for cross coupled NOR gate, NAND gate connection, we added 2 more NAND gates, so that it will output that I mean when I am applying S bar will be coming out R bar, so that inside I am having the exact S bar R bar latch, the default behavior I am getting. So that about it. So this is what we want to say. So this is from the textbook I given you the diagram in detail, so you can refer this, right? So now it is very clear to you. This is a basic cross coupled NOR gate configuration, and where why the truth table is looking lengthier here. It is just like and you know, so one s is equal to 1 is for setting the circuit, fine. And after setting the circuit, if I am applying 0 0 0 0, so that it will retain the information, right? So that is what they highlighted. So retain the information, say after s is equal to 1 and r is equal to 0, retaining means again s is equal to 1 and r is equal to 0. We can either show like that or show in the way I explained. So similarly, when r is equal to 1, it is resetting the circuit, right? Now after this s is equal to 0 and r is equal to 1, so that the circuit is already in reset mode. If I apply 0 0, again it will retain it as it is, and this is something that is forbidden. So they added 2 more rows. Simply they were trying to say that what is this retain. If it is 1 0, 1 0 will be retained as it is. If it is 0 1, 0 1 will be retained as it is. Like that they highlighted. Similarly, the NOR the cross coupled NAND implementation of a basic memory element, here also that 0, here 1 1 corresponds to no change, right? So that 1 1 no change case they explained in 2 rows. I mean, if this one and this one, if it is already in set mode, that will be retained. If it is already in reset mode, that will be retained. So that like that they are explaining. Sorry, reset and set. And this is the same configuration with the enable input, something we already seen, like cross coupled NAND, cross coupled NOR also we saw. Okay, so anyway, so in textbook only this diagram is given. And whenever this enable is 0, whatever be the input, it is simply no change, set or reset. Okay. Now this is something given in the textbook, but I want to tell you it's better to understand it as forbidden state. The state is not allowed, that's all, or not allowed state. Okay, so this input is not allowed. I can't say that the my understanding is like that. I can't say that the output is indeterminate. Actually, you are getting a valid stable output. That is what we saw already. That means when both inputs are 1 1, what I remember is both q and q bar are found to be 0 0. We analyzed it, and the problem is with immediately after that, if I apply that no change case, it is going to an indeterminate state. So it has to be more clear, or for the time being you can understand it as forbidden state. So there is no problem with this input. S is equal to 1 and r is equal to 1 in this case. On the previous case both are 0. Yeah, and that forbidden case means why we are not allowing it, because immediately if we allow, we will get both q and q bar as 1 1. That is a stable output, but immediately after that, if you apply that no change case, you may not be able to retain the information, and also it will go to an indeterminate state. So we need that much clarity on that statement if you are simply writing it like indeterminate. So it's better to write it as forbidden. Hope you understand why. Okay, yeah. Now what about see, if you have any doubt, please watch part 1 to 4 where I am explaining that concept. I am building the concept. Okay, so here I taken the assumption that you already know it, and with that background I am explaining. So those who are watching it directly, please watch the previous part and come to this. So now there is one more variation of this SR latch, that's what we seen. It's called a D latch. It's very simple, nothing, simply this is your SR latch configuration, right? So where is it? This is your basic SR latch configuration, right? So this one, okay, let me draw like this, and to this one I'm removing it. What I done is this is your S and this is your R. Now for this S, I am applying the input as it is, and for R I am applying its negation. Simply I am complementing. So now I have a single input called D input, and that D input I am applying for S as it is, and its negation I am applying for R. Now tell me what will happen. As usual, whenever this enable is 0, the circuit is not activated, right? Now when enable is 1 and D is equal to 0. So this is a case D is equal to 0. So D is equal to 0 means on background S is equal to 0 and R is equal to its negation, because I am applying passing it through a NOT gate. So R is equal to 1. S is equal to 0 and R is equal to 1 is the behavior. R is equal to 1, that is reset. Because now onwards only enable everywhere we have this default behavior, right? R is equal to 1 for resetting the circuit. So circuit will be reset. Now you can say have an observation that this 0 is actually coming as the output. So you can remember like that whenever this D is equal to 0, the output is also 0. On background what is happening when D is equal to 0, S is equal to 0, R is equal to 1, that is resetting the circuit. But as a black box, when you are giving an input to the circuit, as 0, you are seeing that the output is 0. But this is the background explanation. Okay, so that about it. Similarly, let me explain the second case. Yeah, what is it? Let me tell you. Say when I am applying D is equal to 1. So D is equal to 1 means S is equal to 1 and R is equal to 0. And you know S is equal to 1 is for setting the circuit. This circuit will be set. But the thing is that the observation is that whatever your D, and that will be coming as output. So D is equal to 1, the output is also 1, right? When D is equal to 0, the output is also 0. That's all. So this is a symbol. We can call it as say data latch, like D for data, something like that. It's simply retaining the information, nothing else. Okay, D for data. So the data is latched and you are getting the same data. So you are applying D as 1, you are getting D as 1. Maybe after some delay, because it will take some minute amount of time for processing through the circuit and all. Okay. So like that. So it is only having the set and reset case, and there is no other case like retain, forbidden, nothing. Okay, simply the previous circuit only, but we are making it as something having a single input. Okay, and that input will be coming as output. That's all. So some very fundamental form of storage. Okay, yeah, that's all. And this is the graphic symbol of any latch. So typically SR latch you can see like that. So saying that it is active high. So you are having S and R, and here you are getting your Q and its complement, right? That complement is denoted like this. This bubble means from here you will get something complemented. Okay, so that is the meaning. Similarly for S bar R bar latch, typically the block diagram, by looking at this diagram you should understand that this is S bar R bar, because this S bar R bar, that complementation process is actually denoted by that bubble, just like that NOT gate is represented in a short form. Okay, similarly this Q and Q bar here, fine. Similarly this is your D latch having a single input and an enable. So here also you can add enable, no problem. So then that will be a third input in this case, right? And here in case of D input, only a single input and an enable Q and Q bar. So these are all the symbols we are having. Yes, thanks for watching.